Hi guys, I'm Sophia. I'm a co-founder of Bagao.dev. For those who are first time in our meetups, thanks for joining and welcome to Bagao community. I shared link to our Slack workspace. Please join and let's bring the power of community. Today, our speaker is Rishabh Mehrotra, who is a senior research scientist at Spotify. He's based in London. Rishabh received his PhD in machine learning from University College London, and he's a recipient of Google Research Award. And today, Rishabh will share how his team is using reinforcement learning to bring diversity in music content at Spotify. Many of us are users of Spotify, and I'm very much excited to learn how this works and about your research work.
Thank you. Thanks everyone for joining us. Thanks Sophia for the introduction and for the invitation. So I'm really excited to talk about some of the recent work which we've been doing. I'm going to touch upon some of the problems we consider internally, present some insights from some of the offline evaluations we've done and some of the actual A/B tests and deployments we've done. So feel free to kind of type in your questions. I have a separate screen. I can have a look at the questions and I can pick it up while we talk, or if in case we can take it later as well. So we're going to talk about like a problem of track sequencing, specifically to shift consumption to diverse music content. So in this talk, we're going to focus on three things over here. One is like we want to be able to shift consumption, and we want to shift consumption towards diverse music content, and we want to use some of these like reinforcement learning techniques for track sequencing problems in general. So in this talk, I'm gonna just briefly talk about myself and Spotify, and then spend most of the time in going through what does like shifting consumption to diverse content actually mean. So as such, during the course of the talk, we're gonna talk about why is diversity important, the scope for diversity, and what if we just optimize for user satisfaction, and what if we do explicitly encode diversity as an objective, and then like what does it mean for system designers and recommender systems? So in general, you're going to hear some words like SAT. SAT stands for user satisfaction. And we are situating this talk in a recommender system setting. So we're talking about a bunch of items and then like the system deciding what content to show to the users. So that's the general background. And I'm going to kind of provide accordingly some more specific details as we go along. So yeah, as Sophie mentioned, so in general, like I'm part of Spotify in London. So we have a research lab. We have a bunch of, we have huge presence in London, Stockholm, New York, and Boston, and a bunch of other places as well. In general, I'm mostly interested in like machine learning for marketplaces and user behavior modeling. So again, like if any of these are interest to you, please feel free to get in touch. Just kind of situate some of this work in the broader spectrum of the work which we do at Spotify so that you have more understanding on where we are coming from. So my team's mission is to connect listeners and creators in a unique and enriching way. So if you look at this diagram over here, then we're connecting the fans with the artists, right? So this is not just the case for Spotify, but a lot of these unicorn companies coming up are these marketplace platforms. So marketplace platforms are multi-sided platforms which are connecting the users, the consumers of content with suppliers. So for Spotify, it's artists. For Uber Eats, it's like the delivery partners and restaurants. For Airbnb, these are the room host and so on. So again, this is a general, very broad setting that we often need to develop recommender systems which can expose content to users, but also these systems should kind of care also about the suppliers of the platform itself, right? So in general, like what we talk about are about some of these recommendation problems at scale. And very interestingly, very importantly, if you look at the number of tracks, these are like about 70 million tracks, right? So that means recommendation is a hugely important problem here. That, I mean, there's no way people can explore this large amount of catalog. So looking at the context and recommending the right content is of prime importance to us. And we do that via different recommendation products. So you can look at playlist, and the playlists differ in their listening patterns. So you might want to consider ranking tracks in a playlist, or like which playlist cover to show. A lot of these personalization problems exist at Spotify. You can look at radio sessions. So radio sessions are, you can start a session, and these are more of a sequential recommendation setting if you're looking at machine learning problems. We can talk about search. So searching has a specific platform. So a lot of these like traditional search and information retrieval problems pop up when we try to handle search at Spotify. We can look at homepage. So home presents a holistic experience. And again, it's the first screen you see when you open the app or use the desktop. And this is about like playlist ranking on the homepage. Again, a bunch of very important, interesting machine learning problems. And different genres and moods can be viewed as subhubs. So again, like you can personalize some of these as well. So in this talk specifically, I'm going to focus more on the playlist and track level ranking. We have a bunch of work published and productionized on the homepage. So if you're interested, you can look at the Spotify research website or some of our publications for that. But today, in the next 45 minutes, I'm going to focus more on how do we sequence tracks for a user inside a playlist, or how do we sequence these tracks in a radio setting. So radio is a sequential interaction session, and the goal is track sequencing. So we want to sequence tracks and try to give diverse content to users at the same time. So first of all, like, why do we care about diversity so much? And basically in the next 5 minutes, in the next 5 to 10 minutes, I'm gonna talk about why is diversity important for us. And then like, what's the scope for diversity? Do we even have content wherein we can get away with showing diverse content without users kind of, the users might like it, might not like it. Let's see what that turns out to be. So why diversity? So in general, we had this paper at the web conference in 2020, wherein we were exploring the algorithmic effects of diversity of consumption. So we want to understand users' consumption diversity and see, okay, what's the impact? Are people getting diverse content? Are they not? Are they happy with it? Are they not happy with it? So this kind of serves as the motivation for our ML work, which we do later on. So in general, we found some really nice analysis here. So one is like, we found that different users differ based on their type of consumption diversity. So you can look at some users as a specialist, and these users are like really narrow in their consumption diversity. So they care about a very narrow specific taste of music, and they're pretty much okay with that. Whereas on the other hand, generalists have a much wider horizon of music consumption. So their radius of listening is a lot wider, and then they're like drastically different than specialists. And in general, we have these like nice distributions of users on this generalist specialist spectrum. And as you can see from the figure on the right, that, this is agnostic of the activity percentile. So again, like you may be a very highly active user or a very low active users, but still, we do see that there's a rich heterogeneity of users across these specialist and generalist categories. Importantly, why does it matter? So it matters because we see evidence that the broad listeners, so listeners who have a wider range of consumption, so that means they have a high consumption diversity, they convert more. So convert more, so Spotify has a free tier and premium. So again, like the people who pay for the service, they can convert from a free to a premium user. So we are seeing that like users who have broad in listening, they convert more. And importantly, they churn less as well. So again, this is very interesting because a lot of these platforms care about subscription numbers and care about the user retention. So now we are starting to see some influence that like users who consume diverse content, they kind of convert more and churn less. So again, very important insights for a lot of like business decisions. And very interestingly, we also found evidence that the organic and programmed streaming are slightly different. So what I mean by organic streaming is the user coming in and going to the playlist. And so again, recommendations play less of a role over there. Program streaming is like users consuming content from our recommended products. So again, we are seeing that most of the mass over here is slightly above the y equal to x line. So that means organic streaming is usually broader than program streaming. So that means like we should program the streaming to be broad and diverse. So this is one of the motivations why we might want to consider and explicitly encode diversity in our ranking objectives. So in general, like one night takeaway is like, if you increase the listening diversity, then we observe like better conversion and retention. So there's a question by Neeraj on how do you measure the GS score? So the GS score I mentioned over here, we have a very simple similarity-centric view of this. So again, like we learn the embeddings of the users, we learn the embeddings of the track, and then from those embeddings we can compute distances, and the GS score is a function of the tracks and the distances between these tracks and between the user. So again, like if you look at some of this paper, it has a lot more details about this on how we compute a GS score. Okay, so in general, like just a couple of other points, right? Why is diversity important? For a user, it facilitates exploration of content. So, as a user, I don't want to just listen to the same kind of content. So we kind of diversity enables that. And it kind of lessens the rich gets richer filter bubble style problems on platforms. And in general, as I mentioned, like diversity across genres has been shown to be associated with user retention. But importantly, the last point, it enables platform goals for supply exposure. So again, I mentioned that like Spotify is a marketplace, Uber Eats is a marketplace, like Airbnb, Etsy, these are all two-sided or three-sided marketplaces. And on these platforms, we system designers care not only about the user, but also about the suppliers. So again, in a world wherein users listen to more diverse content, the platform has a chance to expose certain suppliers. So again, the diversity is not just important from a user perspective, but then it's important to the platform because it gives us a way to expose certain suppliers, certain artists who we may not otherwise expose. So again, like as a platform, diversity helps us not only for users, but also for suppliers. Great. So far, hopefully we've kind of convinced that diversity is important, but what's the scope for diversity? So let's look at some actual data and see what's going on in actual user streaming sessions. So basically, in this part of the talk, I'm just going to present some motivating analysis, which motivates the ML model development we do, which we get to in like 10 minutes. So again, as I mentioned, like we are looking at diversity as an enabler for shifting consumption. So shifting consumption means that there is a particular behavior of users and they consume certain type of content. And we want to shift it towards less popular content because we care about like popularity biases. We don't want only the top tier artists to popular artists to get all the music consumption. We want the platform to encourage diverse and less popular content to be exposed and consumed as well. And we want to shift consumption towards content different from users' historic taste. So maybe I've developed a specific interest profile and I want users to kind of, to the platform to give me something more than what I've already listened. And in general, you can quantify diversity in a number of ways, right? You can look at similarity-based diversity. So similarity-based diversity says that I want to reduce the average user track similarity. So if I'm recommending content, which is very, very similar to you, then it's not diverse. So again, we can create these user profiles. We can learn user embeddings and have computer distances between users and tracks, and then see, are we reducing the similarity of our recommendations? We can look at popularity-based diversity with the goal of showing less popular content. So this is going more towards tail. So ideally, if you're shifting consumption, if you look at the distribution of consumption, we want to shift it towards the tail and away from the head. And we can also look at within set diversity. So again, like if I recommend you 10 tracks, then are they very heterogeneous? Are they homogeneous? Are they diverse among themselves or not? Again, there's a lot of definitions in which you can define and quantify diversity. In general, in this talk, we're going to focus on the first two, like similarity-based diversity and popularity-based diversity. Great. So in general, if you look at a random set of tracks, right? So these are the two distributions. So there are enough tracks which have low similarity and low popularity. So that means it's not a data availability problem. We have enough tracks which we could recommend. And this is very expected and obvious. But again, just a plot to kind of speed you up this bit. If you start looking at some correlations, right? So on the right, we're looking at track level correlations. So we look at the user tracks for a track, we compute the user track similarity, we compute the popularity, and then whether this was relevant to the user or not. So again, by relevant, it means like the user streamed the track. If we showed that track to the user and the user skipped the track, that means it's not relevant. So we see that in general, like similarity is positively correlated with relevance. So in general, this is expected that users like familiar music. And if we show them that, then I mean, their satisfaction it's correlated with how similar tracks we show them. So if we reduce the user track similarity, then it can potentially harm user experience. And popularity is not correlated with relevance much. So again, like we see that it's more likely that you can reduce popularity and still get away with it without harming user experience. If you look at the right, which is session level correlation, then we see that popularity diversity is not correlated to session length or average relevance. This is a great thing because if popularity diversity is correlated with session length or the average satisfaction, then it will be harder for us to play around with it. And for similarity diversity, we say that, interestingly, it's not correlated with session length as well, which is a great thing. Why? Because if I can show less similar tracks and still my session length doesn't decrease, then that's a good opportunity for us, right? So again, all good points so far that we really should try to do this diverse recommendations. Finally, let's look at some heat maps. On the x-axis, we have satisfaction. On the y-axis, on the left, we have popularity. On the right plot, we have similarity. And in general, okay, things on the top means that they're highly popular, and things on the left mean they're like less satisfying. So if you look at those red boxes, so these are like top left, right? So that means they have a high popularity and high similarity and low satisfaction. So that means users often are not satisfied with popular content with most similar content. And interestingly, there is enough mass and density there in the bottom right. So that means there are content which is less popular, which is less similar, and users love it. So that means, again, all of this is just to say that there's a lot of scope for us to do this in a good way and without hurting user satisfaction. Great. So far we've looked at that we want to show diverse content, and we have a few reasons to do that. And from the preliminary analysis of the data, we find evidence that we can do that. I mean, there's enough data-centric analysis to show that we can do that without severely hurting user satisfaction in the short term. So let's go into talk about like how do we do this diversity-aware recommendations. So the main task which we'll be focusing on for the rest of the talk is the re-ranking task. So basically, we have a bunch of candidate tracks for a playlist, for a radio session, and these are a few thousand to a few 10,000s. Again, we do this two-stage ranking wherein we select a few tracks, and then they come and be part of the candidate pool of tracks we have. And then the goal is from that larger candidate track pool, can we select these tracks and rank them to create the playlist for the user? So that's the main task we're going to be focusing on. So again, this is a ranking task. So all these metrics like NDCG and all those are the metrics which we'll be interested in the offline evaluation. So just some brief background. So for each session, we have a number of sessions. For each user, we have a number of sessions known. A session consists of a series of tuples, which are like track and the user feedback. So again, like for each track, because this is sequential recommendation, we know whether the user skipped the track or streamed it completely, or like how many milliseconds did they stream. So we have that feedback for each track, and the task is to re-rank a given session such that the relevant tracks are recommended first. And again, as is typical in the ranking evaluation, we can look at the top K recommendations and compute the metrics we want. So 2 questions we are going to focus on in the next 20 minutes. The first is, what would rankers who are solely trained on satisfaction, how would they fare on diversity? So again, we have a bunch of rankers of increasing complexity. So you can start with something similar like just similarity rankers, and then have neural rankers, feedback-aware, and reinforcement learning ranker. And the first question we want to ask is like, how do they perform on satisfaction, but also on diversity? And then go on to the next question, that how do we explicitly encode diversity into these models? And we're going to talk about like 4 different approaches, which we covered in this work. Great. So we're going to focus on how do we rank tracks without focusing on diversity, just to see how it performs. But how do we do the ranking? So we're going to talk about 4 of these methods, and they are methods of increasing complexity. So again, you can consider the first couple of them as baselines, and 3rd and 4 as like more sophisticated approaches to model the ranking problem. Okay, the simplest thing first, right? You wake up in the morning and you say, okay, how do we rank tracks? So you can sort tracks based on user track embedding vector similarity. So a bunch of work goes into developing this, right? So you'll have to have a representation for the users for the tracks, and they have to be in the same space so that you can compute your vector distances. So we use something, again, like we developed our own embedding-based approaches, and we can look at playlist as documents and then try to mimic some word-to-vec style embedding approaches. So again, we have a few papers published which talk about that in more detail. But assuming that you are able to learn these embeddings, you can just compute a cosine similarity and then sort by that. And that's the first ranker, right? Very simple, no ML model training required. There's no feedback awareness. It's not adaptive at all. It's not learned. It's just a greedy sort by cosine similarity function. What next you can do is like have a simple feed-forward ranker. So we have a neural ranker which have some track and session level features. So again, like you can look at, the features of the user. Okay, what kind of features could there be? So there could be some user features, which are the user embeddings or some other quantified features. There could be track features, and then there could be user track interaction features, because we have the historic interaction data on users and tracks, and then we can kind of consider those features. And important with that, we can look at session level features. So the session level feature would include a lot of metadata about the playlist. So if you're in the, let's say, all out 80s playlist, So All Out 80s is like nostalgic music for us. It's like 40 years old, 30 to 40 years old. So again, like different types of features are going to be important in that playlist. But if you look at songs to sing in the car, so this is more like a very like happening playlist and like All Out 2010s. So these are like more recent playlists, and different types of features are going to be important. So we group all of them into the metadata we have on the playlist, and then you can just put your favorite neural network on top of it and then train a model. So we have this playlist embeddings, which are learned as part of the network itself during training. You can predict on the probability of the user skipping a track. So that's the feedback you have. Did the user skip the track or consume it? And that's your label. And you can optimize them using a standard cross entropy loss. So again, nothing fancy here, just a typical simple first attempt of a neural network to see how well this will perform. And again, once you have these scores, you can just greedily sort by them and trade your ranking. So the caveat over here is that it does not consider user history directly, right? I mean, it's indirectly aware through the user embeddings, but then like, what has the user been doing in the recent past? Have they skipped some tracks which they usually would have liked or not? So again, like we're not considering that feedback in this model. So this leads us to the feedback-aware rankers. So the goal over here is that we want to incorporate users' previous sessions and the feedback. So here the user comes into the platform, they've had a few sessions, and in each of these sessions, they have listened to a few tracks across different contexts, right? So it could be some playlist 1, playlist 2, they went on search, they came back on the homepage, and they have kind of moved around a bit. And we want to summarize each session and then use the feedback the user gave in those tracks, and then kind of use it to make better predictions and better ranking. Great. So what we do is like we create something we call the session summarizer. So again, it's composed of the track features, the relevance label for each, did the user skip it or stream it, and the metadata for the specific playlist. And because it's a sequential model, it's a session, so we can pass it through LSTMs and then have an attention layer at the top. And then the output of that will be the session representation. So again, what we've done so far is we've tried to look at the past sessions, and for each session, we can have an internal representation, which would be the summary of the sessions which the user interacted with. And we can do that for each session, right? So this is for one session. So one session is a sequence of tracks, and this session summarizer gives us what's going on in that session. Now let's look at the user feedback across multiple sessions. So in general, once we summarize this session, we can learn a dynamic user embedding. So the dynamic user embedding would be composed of the user feedback across a number of sessions. So again, like based on how well you're able to get access to real-time data and like how far do you want to go, you can look at the current day, a current few hours, or like last few sessions. So based on that, you can look at a multiple sequence of sessions. We already have for each session, the session summarizer information. So now we have an embedding, a representation for each session. We tag it with the metadata of that playlist, of that session, and then pass it through the attention layers. And that gives us a dynamic user embedding. So what's going on over here is that, again, what we have so far is that we summarize the session first, and then we looked at the user sequence across multiple sessions, and then created this dynamic user embedding. Great. So we have this so far. And what we then do is we can train a neural network using all of these components. So we have the session summarizer. We then use the session summarizer inside the dynamic user embedding to get a more recent user view of the world. So they might have been skipping a few tracks, they might have been like hiding a few tracks and so on. And based on that, we create this dynamic user embedding, and then we pass it on to this neural network, which again, we train in a similar way. So we train with cross entropy loss based on the label, which is a skip or not. Great. So this gives us a feedback-aware ranker. So again, we started very simple, right? We started with a simple model of a cosine similarity. We trained a simple neural model. And then we said that I want to look at users' recent history and I want to incorporate feedback. And then we created a session summarizer, we created dynamic user embedding, and then used them to create this feedback-aware model. So again, that's the third model. Finally, what we want to do is like, we want to see like, okay, what would like the reinforcement reinforcement learning ranker offer over here. So again, we're not going to create this IL ranker from scratch. We already have these modules which we're going to reuse over here. So we have the session summarizer, we have the dynamic user embedding, and we have the FeedbackAware model. These are modules which we can reuse in the IL ranker. But importantly, how do we formulate this problem as an IL ranker? So again, there's a lot of work around like model-free, model-based reinforcement learning, and a bunch of others. And here we take a simple approach. We say that the reinforcement learning ranker is formulated in terms of a sampling. So we have a pool of tracks, and the action, typical IL setup, right? So we need the states, we need the action, we need the reward. So the action is the sampling probability. So the action is like, I want to be able to look at a candidate pool of tracks and sample one track at a time, and then create that sequence. So that's the sampling-based RL philosophy we go in with. So in general, the RL formulation for us says that we want to learn a policy, which is pi, which is like given a state S, what's the probability of like sampling this track T? So the RL policy for us gives us the probability of sampling a track given a state S. So we need like the track and state representations, right? So what are these? So T is just a typical track features plus the derived features from the FeedbackAware ranker. So again, we have already trained these FeedbackAware ranker, which gives me what's going on in the recent history of the user. And that gives me the set of representations I need for the track. And then the state representation for my current context would be a concatenation of the previous tracks in the session plus the session metadata. And then we can encode them using stacked LSTMs. So if you look at the part of the model on the right, so we're looking at a few of these sessions, and we're looking at a few recent tracks. We pass it through the LSTM, and then we concatenate it with each potential tracks. So basically what we've done so far is like, we said that this is how we reuse the modules we have and get these state representations. Great, that gives us the first part. Now, as we mentioned that we're gonna have a sampling-based IL ranker. So to sample a track, we need a logic. So we need the probabilities based on which how we can sample from a pool of candidate tracks. So again, like to get us to sample a track, we get the logic for each track, and the sample probability is the softmax over these logics. So again, like to sample, we can sample a track, we just kind of draw from that probability distribution. So what does that look like? So the logic is over here on the right. So far we have defined the state representations, and then we looked at the recent history of the current session. We pass it through an LSTM, and then for each potential track, we can concatenate it, pass it through a linear layer, and then get my softmax over the logic. So that gives me the probability distribution for each track, and then like I can use them and sample one track at a time. Great. So we have defined how we're going to sample. We have defined what the states are. What's the reward? So again, like for now, we're going to keep it very simple. We're going to say that let's have a very simple binary reward, like 0 if a track is skipped, 1 otherwise, and we add a small constant, which just to ensure that like we assign negative rewards to non-relevant tracks. So again, this reward formulation is fairly simple. We've had a publication like at the web conference in 2019, wherein we tried more user and content aware reward. So again, like there's a lot which we have extracted internally by just playing around with the reward function and like defining it in a good way. So again, if you're interested, you can look at some of that work from our group. Okay, and then like once we have this, we can train using the standard reinforcement algorithm. So this is like really, really dated, but that's what we use to train the model. Okay, so just a quick summary of where we are. So we've said that we want to understand the interplay between model complexity and performance. And in general, we've looked at like 4 types of rankers. So we started with something simple, cosine similarity, and then we matured to a neural ranker, a feedback-aware ranker, and the other ranker. The question is, how do they fare on diversity? So quickly looking at the results. So again, like in the paper, we have more results on NDCG metrics as well. But again, I'm just presenting a small table over here. So we see evidence that the SAT metrics, so SAT stands for satisfaction. So the satisfaction metrics increases with increasing model complexity. And again, these are not like huge differences, but the problem over here is that you're re-ranking only interactive tracks. So if you're re-ranking the entire pool, then you will see more nuanced differences. So again, these minor small wins in our offline metrics, they translate to a lot higher metric wins in the online world. So again, it took us a while to get our offline online correlation set up. Again, I would love to talk about that in detail, but that's beyond the scope of this talk. But definitely just a plug-in to say that it takes a lot of effort on getting a correlation between your offline evaluation and the online A/B test results. So again, like we spend a lot of time doing that. And once we had that, then it was like really beneficial to kind of pick up the right A/B test treatment cells to kind of test out on live users. But again, like some of the other things we noticed was that increasing model complexity worsens popularity. So there's a big jump in the popularity score, which is bad because we want to diversify. We want to reduce the popularity. And as we increase model sophistication, we see that the models do worse on the popularity diversity. And in general, like it's expected that more complex models leads to like less diverse content as well. So in general, again, the cosine similarity by definition will give you the highest. But beyond that, we see that as we go from feedback to RL or from feedforward to feedback to RL, we see that the similarity is increasing. So the takeaway so far is that as we increase model complexity, it gives us better offline satisfaction metrics. Again, we saw similar results for NDCG and other metrics, which are in the paper. But it is coming at the cost of diversity. So again, that means like if we want to diversify our recommendations, then we want to explicitly encode them in our models. So that's where we are. Just a quick time check. Okay, great. So in general, the quick summary so far is that we've looked at a few of these rankers. We started with simple models and then matured into an RM setup. And we've kind of seen that like more complex models perform worse on diversity. And that motivates us to explicitly encode diversity as an objective. We're going to talk about a few ways in which we could do that and then see how they perform. So the simplest thing to do is just interpolation. So you have an interpolated score between your satisfaction score and your diversity score, and your alpha parameter controls the trade-off between relevance and diversity. Again, nothing fancy, super simple. For your S, you can use any of these rankers. So the output from any of these rankers could be the satisfaction or similarity relevance score. And you can look at the D as the diversity metric over here. And again, like with alpha, you can control this, how much you want to trade off one for the other. Great. So this is the first simple approach, like we can interpolate. We also kind of formulated this problem as a submodular function. So again, like I would not have like huge amount of time to discuss the submodularity in detail, but it's a very fascinating concept, which we've kind of applied in a few settings internally, and it has given us some very promising results as well. So submodularity as a function, as a philosophy, says that these functions exhibit diminishing returns policy. So again, like oftentimes when you have a larger set, then upon incrementally adding one element to that larger set, the value, the gain in the value you see, that diminishes. So if you look at the equation, then Y is a superset of X. So X is like a subset of Y. And if you're adding something, if you're adding the same item to a subset, then the value of the gain, right? So you have the set with this item, which is like X union small x, and you have the function without this item. This delta is bigger for the subset than it is for the superset. So in general, a quick example would be that like friends, like if you're on Facebook and if you have, again, just a hypothetical cooked up example, but if you have 0 friends or 0 followers on Twitter, then the first follower will be a huge gain for you, right? And going in from the 5th to 6th follower will be more important. But if you already have that like 10,000 followers, then going from 10,000 to 10,001, that delta will be like not much for you. So this is submodular function. And in general, why we love it is because if you're able to formulate your problem as a submodular function, then there is like greedy solvers over there. And I mean, they have some theoretical properties that a greedy solver will go as far as like 1 upon E, 1 minus 1 upon E in terms of optimality. Again, not much, we can talk more about this in this specific talk. It deserves another talk in itself. But now the question is like, can we formulate diversity as a submodular objective? And there's a lot of work like diverse summarization, a lot of work in NLP and machine learning has gone into creating these submodular functions. And then we kind of created a submodular function of our own. So we said that given a set of tracks, we can define a submodular function in a combination of the relevance score and the diversity score. So in general, the submodular function prefers tracks with highest relevance, but also like maximizing the distance between the tracks we already have. So in general, the submodular function tries to encourage diversity. There's other ways of defining submodular functions, but again, we're not going into much details here. And the solution, once you have a submodular function, then you can just greedily pick up tracks which maximize this function. So that's the best part. Like once you have a submodular function, you have theoretical guarantees on its optimality by just greedily maximizing this function. Quickly, the third thing we could do is like just interleave. So by interleaving, we mean like you have a list of just satisfaction tracks, you have a list of diversity tracks, and then you can try and combine them together. And then you can, there's a lot of work in the interleaving in the SIGIR and KDD community around how do you interleave, and you can do probabilistic interleaving and like multi-leaving and all of that. So we applied something simple from that, and you can then create a final list. So the final list is an interleaving of your highly relevant tracks and some of these diverse tracks. And finally, we can say that, okay, we have an RL model. How about we just kind of tweak the reward function? So we did some experiments internally on coming up with different reward functions. One of the best performing ones was this one. So again, like the RL allows us to easily tweak easily is an understatement, but we can tweak the reward function and add a diversity term. So here, what we're saying is that the reward which performed best for us was a combination of the relevance. So relevance is the user is skipping this track or not. So there's a user U and there's a track T, and did they like it or they did not like it? But it is a function of diversity multiplied by relevance. And this is important because like we don't care about diversity just for the sake of diversity. I mean, I can pick up one track which is very different from what we've listened so far and just throw that to you, right? And that's not going to be useful because, again, I mean, just enforcing diversity is easy. Enforcing the right diversity is tricky. So what we do is like we multiply the relevance with diversity. So we only care about diverse content if it will be relevant. So again, that's the reward function, which we had a simple 0, 1. We now have this like a multiplying factor between this diversity and relevance. Again, it's an easy, simple thing to follow here, but the moment you introduce a multiplying factor into your formulation, then weird interaction effects happen. Because the R over here is a binary function, then we get away with it. But if you have a more continuous reward, like the relevance is not 0, 1, if it's between 0 and 1, then you have weird interaction effects between the D and R over there. And then you have to kind of control for that. So just a few heads up on some of the things we found internally. Great. So let's look at how does it perform, right? I mean, so in general, what we've seen so far is that we've looked at how do models which are just trained on satisfaction without diversity, how do they fare? And we found evidence that like these models worsen diversity. So we have explicitly looked at how do we enforce diversity in our modeling. Great. So if you look at the 4 diversity approaches we compared, we can fix the ranker. So we can, let's say we use a feedback-aware ranker and we vary the parameters. Let's see which one performs better. So now we're going to see a lot of these like scatter plots. So on the x-axis is satisfaction metric. You can replace hit rate by NDCG. We have very similar results. So things on the right would mean higher satisfaction. Things on the bottom would mean lower popularity. That means higher diversity. So ideally, we would love to have something on the right bottom, because things on the right are high satisfaction, things lower are high diversity. Great. So first of all, we see that the RL model gives us the best trade-off between satisfaction and low popularity. Why best trade-off? Because you see like they are further on the below and the rightest, right? So if you look at these curves on performance, then the blue dots are the RL model and they're farther right and they're kind of further below the other plots. And interpolation kind of gives a second best trade-off. Submodularity fails to decrease. I mean, yeah, submodular performs like quite worse in our experiments. But I just want to openly mention that this is not to say that submodular functions don't perform well on this problem, but more like that the way we define submodularity, that doesn't perform well. So I'm sure like people should invest time in like coming up with better submodular functions, and then they might get better results. And importantly, like if you take a step back and look at like there's a decent amount of trade-off over here, that like there's like a significant change in your satisfaction and significant change in your diversity metric. So that means this is great. I mean, it could have been a lot worse. Everything would have been concentrated between a very narrow region. That means as a system developer, I don't have a choice. Here, I have a choice. If I want more diversity, I can have more diversity. And this trade-off is like really nice for your product managers and like business decision people to kind of pick and choose on what kind of model you want to ship to users. If you look at similarity diversity, then the interpolation and RL give very similar results. So again, up until now, we are looking at popularity diversity. We're switching to the similarity diversity. And the interpolation gives a much wider range of trade-offs. So again, like this is encouraging because we prefer more trade-off, more ranges over here. Again, the submodeler doesn't manage to give any useful trade-offs, and then the hit rate difference for fixed diversity is notably larger. What does it mean? So it means that from the left to the right, the difference over here is larger than what we saw before. That means if we try to induce diversity on similarity, then that's going to have a more detrimental impact on user satisfaction. So again, the range on the x-axis shows how much are you impacting satisfaction. And if that range is higher, then that means like you're impacting satisfaction more. If that range is low, then that means like, yeah, not much satisfaction is impacted. So the takeaway so far is that for popularity diversity, the RL performs better. And for similarity, interpolation is fairly competitive as well. The question is like here in this experiment, we had fixed the ranker. But is it just true for all rankers or just for the feedback-aware ranker? So again, we looked at the interplay between ranker and diversity methods. And the key question we ask is, does the specific diversity method work with specific rankers or not? So if we start with popularity, we can try different things. We can look at the interpolation versus RL, the interleaving versus RL, the submodel ID versus RL. So these are three different ways of diversification we have. And again, like I'm not going to dive deeper into details. Like we've spent like 2 pages talking about that in our paper. But across all plots, you see that the red is better than, the blue is better than the red, is better than purple, is better than green. And as I mentioned, that things on the right, things on the bottom are preferred. So that means in performance, like the RL model is performing much better than the feedback model and so on. So that means like increasing model complexity over here is giving us nicer wins, and not just on one metric, but on this like trade-off handling as well. And in general, if I forget about RL, if I look at feedback awareness, then the feedback-aware model is performing better than just the neural network without feedback. So that means like we knew this, right? I mean, like we know that users' recent history should guide your decisions. And if you have a model which respects users' recent history, then we kind of see that it's performing better. The span of popularity is almost the same across all 3 plots. So that means like the ranker almost entirely influences the hit rate. This is a very important point over here, because we're seeing that in general, the popularity, like if you change the diversification approach, then the trade-off you can make on the diversity is fairly stable across the different methods. So importantly, the ranker is impacting the satisfaction, which is what we want. We want to be able to create more sophisticated models to improve user satisfaction. And we are seeing evidence of that over here as well. So finally, the trade-off is like the overall takeaway is that RL up until now kind of provides a better trade-off than others, and interleaving as a way of diversification is a close second. So this was again popularity. I'm going to just kind of present one point and then summarize it all. Importantly, like if you look at the result over here on the left, and so if you look at the result on the left, and if you see the range on x-axis over here, so that range is a lot bigger than what we saw before. So when we were just optimizing for satisfaction, when our rankers were not given any diversity objective, then the difference in satisfaction metric was less. And now in a scenario wherein we care about diversity, the difference across rankers on satisfaction metric is increasing. So this is to say that we are seeing bigger differences in satisfaction than when we only consider satisfaction only models. What does it mean? It means that the choice of ranker is more important when you're considering diversity than when you only care about satisfaction. So again, this was one of the nice takeaways we had, that like as a system designer, as a product manager or a product owner, if you want and if you care about satisfaction with diversity and other attributes, then the choice of ranker is even more important, because the extent to which you can have improvements is bigger. And if you only care about satisfaction, then sure, there are gains to be had, but the difference may or may not be that huge. The moment you have a multi-objective problem, then the sophistication of the actual model is more needed over here. And just on this note, I mean, again, the focus of this talk is diversity and reinforcement learning, but we have spent like close to 2 years now doing a lot of research, and we have productionized some multi-objective models in radio. And this is just one trailer that we care about satisfaction and diversity. But at the same time, you can care about discovery, you can care about connections, like you want users to discover more content. You want to care about the supplier exposure. So we have had a few works which we have published and we have kind of productionized internally, wherein we deal these as multi-objective machine learning problems. And we've tackled them using multi-objective bandits, we've tackled them using multi-objective general ML models as well, and some reward formulation work. So again, not in the scope, but then if you're interested, yeah, some of the references should be on the publications or from our Spotify research website. Great, so to summarize and takeaways. So the take-home message is that from the data analysis, we've seen evidence that there is a scope for showing less similar and less popular content. And from the analysis, users seem to be okay with it. We saw evidence that increased model complexity gives slight better satisfaction results. And the RL model performed better than feedback-aware, and incorporating feedback was more useful than not incorporating feedback. And all of these are better than a non-cosine similarity model. The different trade-offs exist for different diversity metrics. So for popularity, RL is better. For similarity, interpolation is a close second, or it's very close to the RL model. And the choice of ranker is more important when you have additional objectives. And this is just 2 objectives. In production, like some of our radio and other systems are looking at discovery, that I want users to discover more content. I want users to have short-term satisfaction. I want to expose some tail artists as well. So some of our production models are really multi-objective. This is just 2 objectives. When you have 4 and 5 objectives you want to optimize, then like multi-objective ML modeling is really kind of needed. And as I mentioned, like we've done some work on that as well. Great. So let me just kind of briefly touch upon, like as system designer, right? Like what does it mean for me? So first, it means that if I have to develop a first solution, right? So of course, in different companies, different product teams will be at different level of maturity. Some of them would be really advanced. They would have good deployed models. They would have good offline-online evaluation, counterfactual evaluation, and all that set up. Versus some other teams might be really starting up, right? It's a very simple model. I want to have a first ML style model in production. So again, like cosine similarity is a great first solution, especially if satisfaction is the only goal. It's easy to implement, no training required. The neural ranker gives us boost in satisfaction metrics, and it's starting to show more pronounced differences when you consider diversity as an objective as well. And in general, the RL ranker is giving promising results, but then like depending on your ML infrastructure and systems, it could be hard or less hard to deploy based on the specific maturity of the team infrastructure. In terms of ways of diversification, we say that like if you're looking at less similar content, then interpolation is fairly competitive with RL. But if you're looking at popularity, and platforms do care about popularity because we want to expose all suppliers and not just the popular content, then the RL model is better. And in general, a caveat, we know that it might be non-trivial, again, based on the team maturity. Some of these teams are mature, so it's, not trivial, but still like it's less non-trivial than. I mentioned consumption shifting at the start of the talk, right? And this is some of the data from our actual test internally to show that we're indeed shifting consumption now. So shifting consumption means on the x-axis, we're talking about the diversity, and things on the right means things are more diverse. So on popularity diversity, the plot on the top right shows that if the distribution is towards right, then that means less popular content are getting recommended. So that means like we are exposing enough tail artists to the users. And we see over here that for both of these, we're able to shift consumption towards the right. So that means we are able to shift consumption towards diverse content. And so far without hurting satisfaction. Now, hurting satisfaction is a question mark over here because what we've looked at is like one view of short-term satisfaction. What does that mean for more nuanced satisfaction? What does that mean for like long-term satisfaction, long-term return rate? All of these are things which we haven't touched upon in this talk. And finally, serving time, right? I mean, we often have milliseconds constrained when we are creating these playlists and showing to users. So again, systems have these constraints. Complex neural network models need more inference time. So again, like when we increase the complexity of the neural network, then like, yeah, the inference time increase. But also like you have a sequential nature of feedback. So because it's a sequential setting, then you have feedback available. Now, do you want to consume that immediate feedback, or do you just want to rely on this morning's feedback? So again, some teams would have infrastructure which supports these real-time features. Some teams won't. So based on that, you can kind of pick and choose from the different methods so far. So that's the end. And thank you so much for attending. And I think there are a few questions. I will hand it back to Sophia.
We have some questions. Guys, so we have questions on chat that I will read. Also, if you want to ask Rishabh directly, you can unmute yourself and ask your question. So I will start with the earliest question then. Wibor is asking, do you guys have publicly aware data sets for music tech research?
Yes. Oh, yeah. I'm sorry. I usually include a slide on the 3 data sets we have, and for some reason I couldn't do it today. So we have three to four major data sets. One is on 1 million playlist. So we have data set wherein like we've looked at users, 1 million users playlist, and then kind of in an anonymized fashion kind of made it publicly available. So you have playlists, you have a bunch of tracks in that playlist, and then you have some metadata over there. So that's great for set construction and like embedding learning and a lot of these applications. We have a very nice data set, which I was a part of the release, is this 1 million sessions data set. So in the 1 million session data set, what we have is we have 1 million user sessions and the user interaction information on each track. So again, it's all anonymized, but then oftentimes we don't have actual like user interaction data on the public data sets. So the 1 million sessions data set will give you that user sessions and user feedback on those sessions as well. So again, great for personalization, great for sequential machine learning problems. One of the teams internally have recently released this podcast data set. So we have about close to 100,000 podcast episodes, the audio transcript of those episodes, and the actual audio itself of those podcasts and some metadata. So again, like in podcasts and music, we have quite a few of these data sets. And I'm happy to kind of post a link to that later.
So basically, where to find those data sets? Are they on Kaggle or somewhere else?
So these data sets are hosted on, like, some is on AI Cloud. I think the links to those will be on the Spotify research website. So I can just drop a link to the Spotify research website, and
I will also,
some of these should be available there.
Hey, Rishabh. Hi, Sophia, could I ask a follow-up question, if you don't mind?
Yeah, sure.
Yeah, hey, Rishabh, great talk. Thanks a lot for that. I also wanted to ask, like, sometimes there is copyright restriction for the songs for data sets. So generally they limit the song duration to, let's say, 30 seconds or so. Or sometimes they only provide the features, extracted features for a song in the data set. So do we actually have like full-length tracks in the data sets, or is it just extracted metadata from the
so great question. I think in the first data set, I think it's just like track metadata, and it may not have the audio information. For the million session track data set, I think like you're sharing the track features across some of these features are averaged across the entire like rolling window of 30 seconds, right? So again, like some of these acoustic features like tempo and beats and instrumentalness, I think like we're looking at the entire tracks. So I think it's a mix. So for the million sessions data set, some of these tracks have a longer, for the entire duration, the features calculations, but some of these tracks have just for like 30 seconds. So I think it's a mix. But the best data set I would recommend, without knowing much background context on how you want to use it, will be the 1 million sessions playlist, 1 million sessions data set. Yeah.
Cool, Rishabh. Thanks a lot for the answer.
We have question from Elmar, and also Rain upvoted this question. It was in the beginning of your presentation. How do you know that this link between diversity and conversion rate is causal?
Yeah, causal. Yeah, that's a great question, right? I mean, like, absolutely love this question. Like, it's not. I mean, to be honest, like, I mean, we don't. I mean, in this work, we don't. So, what would it take for us to make a causal link over here? Let me just kind of here, right? Yeah. So convert more churn less. So I mean, so we have controlled in this analysis paper, we have controlled a lot on the aspects we could control. But ideally, like we've run some tests internally on showing more diverse content and less diverse content. But then like you face some really interesting problems on heterogeneous treatment effects. Because across a period of time, if you're looking at user churn and the user churns after 2 months, then a lot of things have happened in these 2 months. And in order to disentangle the effect of some of your interventions from the other interventions going on, then like it's a hard problem, right? So it's a great point you've raised. In this work, the findings are not causal. They are controlled for a number of aspects to the best we can. We've done some internal tests on like just like randomized, I mean not randomizing, like randomized user allotment to treatment and control, and whereas the treatment is some form of diversification, some not. But then like there's a lot of things you have to account for. Like let's say if you do run a test on the homepage, then users only a limited content consumption is from the home. They might go to search, and then on search they might find some diverse music, right? So again, like doing it across the spectrum is a hard problem, and we face some tremendously interesting problems on multi-objective, heterogeneous treatment effects and like causal impact as well over there. So yeah, I mean these are fairly non-trivial problems. So it's a great point to mention that.
Mm-hmm. So I see a question from Massimo. Also, it was referring to like somewhere in the middle of your presentation, where the session summarizer, dynamic user embedding, and feedback-aware model trained together end-to-end using listener skips.
Yes, so there are 2 points here. Like the feedback-aware ranker that trains them end-to-end, and I have one of the best points from this work just to mention. So if you don't care about RL model, if you just care about this, then yes, these are trained end-to-end. And I mean, yeah, I mean, you back propagate all the way back and everything is differentiable. So the 2 points over here. One is like everything is differentiable because we're looking at a track level model over here. Recently, we started to work on set level models. So the moment you have multiple sets and you want to kind of output the entire set together, then that means there's a sorting operator, and sorting is not differentiable in a traditional like machine learning way. There are differentiable sorting approaches. There are differentiable ranking approach like operators as well, which we are starting to kind of like look into. But because this is a track level model, this is differentiable and we trained it end to end. You didn't ask this, but like when you move to a set level model, like right now you're making predictions on each track. Instead, I want to put in the entire set of tracks and then make score predictions on the entire set together. That's a set level problem. And set level problems need that set level operator inside your neural network. And that may or may not be differentiable based on how if it's a sorting there, then it's not differentiable by default. So again, there's some work to be done over there. There are papers at ICML last year, which are like differentiable sorting is their differentiable ranking are coming up. So that's one. The second point I want to make is like the RL model uses these. So what we did was once we have this feedback-aware model, we freeze it. So, and then the RL model uses this, right? So if you look at the figure over here, it's using the FA and things from the previous model. And we found good results over here in the sense that if we don't freeze it, and if we learn it as part of the RL machinery itself, then the RL model for us got a lot overburdened. That now it has to figure out the feedback awareness parts and figure out the RL part and the action selection parts. So it was a lot to learn. So what we did was empirically, it gave us better results. Like you learn this part and then use the learn part in the RL setup. So yeah, hopefully that answers the question.
Mm-hmm. So I see a question from Dale. Do you constantly test different versions of this algorithm in real world? To what algorithm, Dale, are you referring? I assume the reinforcement learning model.
Yeah. So sorry, go ahead. Hi.
Yeah, that was it. Yeah.
Okay. So I think we have a variety of models in production. I mean, again, like as I mentioned, like variety of surfaces to testings on. So some of the work which we did on the homepage are bandwidth models. So as of 2018, like we had we had a contextual bandwidth model in production, and like if you've been using Home since 2018, like then you've been kind of surfaced, you've been served recommendations from a contextual bandwidth model which we productionized for the 200 plus million users across. If you're looking at some of these radio things, then we have a multi-objective model, which is not this RL model, but that's a multi-objective objective balancing model, which we haven't yet published upon. We recently kind of productionized some of that. So again, like we have some multi-objective models in production. We have that contextual bandwidth model in production. So parts of this model are in production as part of the playlist ranking techniques. The RL ranker currently is being tested out. So the results I've reported, these are from the offline evaluation results and not from the actual A/B test results. So, I mean, we made some progress after this work, but then like that isn't like published. So that hasn't gone through the PR process. So unfortunately, I can only allude to that, but like not talk about in detail.
So there's a somewhat follow-up question from Ryan, I see. Is the computational cost kind of affects what ranker do you use in production?
Yeah, it does. I think like, I mean, just again, a back of a hand figure, right? I mean, like 200 milliseconds is like when at least some of the playlists we have to surface, we have to kind of finish everything up. So some of these models, if you want to be sequence aware, then you have to look at what has happened in the first 5 tracks and then make inferences on that. That's a costly operator to do. If you're ranking tracks entirely one set at a time, then that's like slightly easier. If you have a wide and deep neural network, then there's a slight more cost to fetching the different attributes and like passing it through the inferencer of the neural model. So again, like, yeah, I mean, all of these components which we're adding to the feedback-aware ranker, they do add some inference. I just alluded briefly to that literally at the last slide, that some of these do have, the serving time. So we have millisecond constraints requirements for some of these models. And in certain surfaces, it's like maybe like 400 milliseconds. In certain, there's like 150. So again, like there are some models which we could use in one surface and not the other. So there's a lot of that involved over here, which makes sense, yeah.
So George is asking about the paper that you're referring to. I mean, we can share the link to the paper.
Yeah, I can drop that link. Yeah.
Krida is asking, so they want to generate features for their in-house content. Can you share how Spotify does feature engineering?
I don't know how can it's hard to answer that in like a 100-second time frame. There's a lot of ways in which we go about it. Like some of these are okay. Let me answer that in 2 ways. One is like there are some foundational features which a team can develop. Again, this is like I'm not talking about Spotify at all. I'm just kind of presenting industrial perspective. So again, don't hold me accountable for what I say. So in general, like at least in my experience so far, I found that having nice user embeddings and item embeddings, and they kind of updated regularly, being inductive, like new users come in and like your user features are inductive in the sense that like they'll expand to cold start cases as well. These are all nice. If you look at some of the work from Pinterest, so they formulate some of these problems as a graph representation learning problems, and a graph representation learning model is inductive by default, because you can look at the local near neighborhood and then kind of deduce the node embeddings, and you're gonna have a heterogeneous graph of like users and item both. So again, like once you have these core embeddings, then they can be used everywhere, right? The question for you then becomes like, what do you want to train these embeddings on? So if they are very specific to a task, then 100 teams cannot use it, because you are training it on a task. These representations are learned on a task, which is very nuanced to a particular team. So that gives you good downstream performance, but then it gives you this coverage cost that now other teams cannot use it. So I think like we found internally that there's a nice trade-off here, that there are certain tasks which are generic enough. And if you train your representation learning models on those tasks, then a lot of different downstream teams can use these embeddings. So again, like the foundational answer is like you develop something foundational which everybody can use. And now you go on to like more nuanced and more kind of narrow representations for the task. So you can imagine like certain types of class clustering together, certain types of class task clustering together, and then you can do some feature sharing across. So again, like we encourage teams to feature share a lot. You can also feature share, you can just model share as well. Like you can, because of these like multi-task setups now, you can have a task, you can learn a network and then make it available for people to just query real time. So yeah, I'm sorry, like there's a lot more to that, which would take like a lot more time to talk through as well.
Another lecture, I would say. I see a question from Carlo. Did you consider looking at whether users liked new tracks in addition to skipped, not skipped?
Yeah, I think like this is a good point, Carlo. Like, I mean, so users can ban a track, users can hide a track, users can save to their playlist. So again, like a save to playlist is a great thing, right? Because now, I mean, once the user save to the playlist, they can always go back to that playlist and like stream from there as well. So this is a great thing. I mean, we want to do that. Like, I mean, some of these user actions are more powerful than the others. So a stream is just a short-term now stream, right? If you're liking, that means like it's a stronger signal. If you're saving, then that gives you a lot more downstreams. So internally, like we value these signals differently. We had a paper at KDD in 2020, which was looking at how do we learn from like signals, which are some of this are like weak, some of this are like strong. The problem is your strong signals like hearts and bands and save to playlist, these are very rare, right? I mean, less than 1% of times do these happen. Your skips and streams are like fairly common. So now you have a problem that some of the labels are like very strong, but they're very rare. The other signals are very omnipresent, but they're not that strong. So we had a paper in like at KDD, which is talking about like how can you learn from multiple types of peak supervision signals and then like train your models together. So yes, we do. Short answer is yes, we do. And there's like special tricks we had to do to kind of use all of them together. So there's a KDD paper on that topic from our group.
Mm-hmm. So I see some questions about recording. So guys, video recording of this talk will be available. I will share in our Slack. So if you missed it, so you can catch up. So a question from Meher. He would love to learn more about offline and online testing. Like how do you treat model bias that was working before the new model? How much the results differ from offline to online?
Yeah, I love this topic. I mean, I think like this is a discussion worth hours and hours, right? So basically, like few things. One is like you can start again. There's a spectrum of maturity of your offline online setup. So in the offline evaluation, you can just start by simple re-ranking tracks. The problem when you re-rank items is that there's a strong bias, right? There's going to be a position bias, there's going to be a surfacing bias, and all that. But let's say if you have a candidate pool of 100 items and the user only interacted with 7. So for that session, you can only re-rank these 7 tracks because for the rest 93, we never had any interaction data. So there is some work from Google which says that, hey, you can consider those 93 tracks. We don't have user interaction data on those, but then here's a way in which you can compute some of those metrics. So there is some work last year from Google which is looking at that. That's great. What we do internally and what a lot of other companies in the industry do is like counterfactual evaluation. So counterfactual evaluation says that I'm going to log the propensities, which are like some variant of the scores which you have, which made you show that recommendation. So if you have that logging in place, then we can have this unbiased evaluation. So there are these estimators. So these are like metric estimators which are unbiased and they're proven to be unbiased. But what that need is like they need you to either log the propensities and then you can adjust your biases in the evaluation, or just have some randomized data collection. So I think like a lot of companies do this, like some sort of randomized data collection. We'll randomize some of these recommendations and then log what happened. And then we can use this randomized data to either train the models or just evaluate your models. So counterfactual evaluation is a hugely important topic. There's a lot of work. There's a lot of tutorials at SigIR as well on this topic, which like counterfactual evaluation is a key term, which I encourage like you to look at. And we spend a lot of time in like setting up these counterfactual evaluators internally, and then like we're kind of heavily using them in our offline online correlation. And again, why do we need these better offline estimators? Is because like I want to be able to select the right treatment cells for my A/B test. I cannot A/B test like 100 cells, so I want to intelligently pick up the few which are most promising. So that's why we need this like offline online correlation, and some of the counterfactual stuff is like more promising in that regard.
Mm-hmm. So, question from Prashant. Maybe Prashant, you maybe you want to elaborate more on your question. So, what language / framework is used for implementation? Also,
Yeah, that's
mm-hmm.
yeah. That's kind of very team specific, but yes, I think like a bunch of us use like TensorFlow. So Spotify is like majorly on GCP, so we are like big customers of Google Cloud, and yeah, we kind of for research and like for practicality, like you can use TensorFlow, JAX, PyTorch, whatever. But a lot of our production models are like TensorFlow based right now. At least like, again, my view is limited because like Spotify is huge as well. The teams I work with are like TensorFlow oriented a bit more than usually.
Mm-hmm.
Yeah, I was looking in terms of, I'm looking for getting into as a machine learning engineer. So that's why I was trying to focus on what frameworks and languages or cloud platforms if companies are working.
Yeah, so we use, right. Yeah, so we use Scala heavily for the data processing pipelines, and Java for like infrastructure for at least some of the deployments I've been involved with. GCP is like we're heavy BigQuery users and like totally everything on GCP, so that familiarity helps. And TensorFlow is like, at least the teams I work with are TensorFlow based for the ML model deployment.
Okay, thank you. Thanks.
Okay. Yeah, I think that's all. That's all questions. Thank you, Rishabh, very much for your talk. So video recording will be available around like in a week or so. I will share in our Slack. Also, if you want to get in touch with Rishabh, he shared his email and he is also in our Slack. So if you have more questions for him and if you want to work at Spotify, I think this is also the question, right? Our community members can refer to you how to be a part of such a great team.
Thank you so much, everyone, for attending, and thanks, Sophia, for organizing this.